What is light? Is it a wave or a particle? What we probably learned in high school is that light is an electromagnetic wave. This wave is transverse, meaning that the oscillations of the wave are perpendicular to the direction of the energy transfer. We are taught that decreasing the wavelength or increasing the amplitude allows for the wave to have more energy. Now, let's discover something what Heinrich Hertz observed in the late 19th century. When ultraviolet light was shown on some metals, they would emit electrons. These escape electrons are what we called the photoelectrons. When placed in a vacuum, this emission can be observed as a circuit is completed because electrons can reach the anode and current can flow. However, when he tried this with blue light, or red light, or microwaves, it wouldn't work. How could this be possible? The first thing that may come to your mind is that the light is carrying energy. And upon contact with the metal, this energy is applied to the electrons around the metal nuclide. When the electrons receive enough energy, they can overcome the electrostatic attraction of the positive nucleus and escape. You may have realized that all electromagnetic waves have longer wavelengths than UV light, so they carry less energy. This effect shouldn't occur when we are shining a lower energy light on the metals. Photoelectric effect simply does not occur with any wavelengths that are longer than specific wavelength. In this case, it's UV. When Einstein heard about this, he realized that a better description of light is needed. Because if the classical description of light as a wave was true, then turning up the intensity of red light should allow for the photoelectric effect can be explained if we say that light is composed of a fundamental particle, known as a photon. These photons can come in different flavors, all sharing the same properties, such as being massless, but differing in one important aspect: their energy. Photons can be thought of as little packets of a discrete amount of energy, propagating through space and time. A photon is an amount of energy proportional to the frequency of the light. This can form into an equation where the proportionality constant K is actually Planck's constant, a very, very tiny number. So higher frequency light, such as UV, is composed of photons of higher energy. Increasing the intensity of the light is like increasing the amount of photons you are emitting. It doesn't change the amount of energy on the individual photons. We have the value of 3 and photons of value of 5. We have more the value of G. So in total, we are transmitting more energy if we decide to use this group of photons. However, that doesn't affect the fact that the individual photons in group 2 have more energy. Now let's go back to the photoelectric effect. Think of the effect as a bit like speed dating. Electrons meet those incoming photons, but they can only have a conversation with one at a time. Once this photons isn't right for them, they let the photons move on the next electron until they met someone they want to date. They will stay in place so that they can carry on speed dating to find the right photon. If the electron eventually meets the right photon, they rush outside in glee with their new date. So this is how photoelectric effect works. An electron can only absorb energy from photons in a one-to-one relationship. And if the energy absorbed not enough to make it jump to a higher energy level or escape the atom, it releases the energy back as a photons. So, that's all for today. I hope you've learned something.